The objective of this video is to introduce the forward converter and derive its operating principles and waveforms. So we previously discussed the flyback converter, which we said was an isolated version of a buck-boost converter. The forward converter can be viewed as an isolated version of a buck converter. That is, we're taking a standard buck converter and we're modifying it to use a transformer in the single pole double throw switch component. So we'll take an approach similar to the approach we took with the flyback converter by showing the parallels between the forward converter and the buck converter. And in doing this, we're going to develop the operating principles of the forward converter. But first, I want to make a note of where you see forward converters typically used. So flyback converters are used for rather low power ratings, perhaps less than 50 watts, something on the order of a laptop power supply or a cell phone charger. Forward converters are still used for low power, but their power range increases up to about 1 kilowatt. So first we're going to consider a forward converter for the case of an ideal transformer. And I want you to sketch this in your notes because we're going to analyze it and then we're going to show what is wrong with it when you use it with a real transformer. And at that point we'll derive the actual forward converter circuit. But it's illustrative to consider what this would look like if we had an ideal transformer where we have an infinite magnetizing inductance and our output voltage is always exactly equal to Ns over Np times our input voltage. So we sketched our forward converter here, and you see that it consists of a transformer at the location of the single pole double throw converter. And so the transformer primary is connected to the active switch, the MOSFET, and the transformer secondary is connected across the diode, or our lower throw. So the primary is connected in series with our top throw, and the secondary is connected in parallel with our lower throw. And we'll resketch the circuit now using the equivalent circuit of a transformer to show how it is equivalent to a buck converter. So you can see our primary equivalent circuit is over here, and the secondary side attached to the transformer equivalent circuit is over here. And if we work with this just a little bit more, we'll sketch the secondary side by converting that dependent voltage source into an effective MOSFET and diode, so into an effective single pole double throw side. Okay, so we start with the converter on the top. And we've attached this transformer to the output of the top throw and in parallel with the bottom throw. And when we do that, we get the following equivalent circuit. On the primary side, we get a MOSFET connected in series with a current source. Then inductor effectively disappears because its value is infinity. It looks like an open-ended, it looks like an infinite impedance. On the other side, we've got our equivalent voltage source at the output of our secondary, and then we've got our throw, which corresponds to the throw 2 of the original buck converter. And so this voltage source right here is alternating between 0 volts and Ns by Np times Vp, or in other words, it's alternating between 0 volts and the turns ratio times our input voltage or our throw voltage. And so since that voltage is alternating between 0 volts when the MOSFET is off and Ns by Np times our throw voltage when the MOSFET is on, we can draw this as an effective buck converter right here where we modify our throw voltage to be Ns by Np times Vn. So we've taken our turns ratio and we've used that to scale our input voltage. And clearly we know how to analyze this circuit. We've already concluded that in this circuit the output voltage is equal to D times our input voltage, which now we have a turns ratio multiplied by our input voltage, so we get our turns ratio times our duty ratio times our input voltage. And this is the voltage relation of a forward converter. So remember I said that this circuit won't actually work as it is because this assumes a real an ideal transformer. For a real transformer, we're going to run into trouble. And let's talk about what that trouble is. So the problem with this circuit, as it's drawn, is that we have an average VP value. And why is this a problem? Well, it's going to cause a flux linkage to build up. It's going to cause the core flux to be unbounded. Recall that our core flux is related to our primary side flux linkage divided by the number of turns of the primary. And using Faraday's law, we can obtain this value by integrating the voltage that we apply. And for completeness, let's also show how this is related to the secondary voltage, which is going to be 1 over ns times the integral of the secondary voltage over time. So when we consider this circuit and the voltage that's applied across the transformer, on the primary side, we're applying our input voltage across the transformer terminals every time the MOSFET's on, and then 0 volts every time the MOSFET is off. So when the MOSFET is turned on the secondary side, we see Ns by Np times our primary voltage. Let's sketch that waveform. So again, while the MOSFET is on over the interval D times Ts, our duty ratio times our switching period, our primary voltage is equal to Vin and our secondary voltage is equal to Vin times the turns ratio. So what does the flux in our core do? Well, let's say that we're starting at time 0 when the flux is turned off, when there's no flux in the core, everything is demagnetized. The derivative of the flux is positive at time 0, so it'll ramp up. We get to the end of this interval and there's no voltage applied across the core anymore, the flux will stay constant. And then when the MOSFET is turned back on, the flux will start ramping up again, and then it will stay constant, then it will start ramping up again, and then it will stay constant. And so this keeps on going until you saturate the core. You'll reach saturation eventually. And then you're in trouble. Your circuit will no longer work because the core is saturated and you're not able to change the flux linkage of the coils any further. So why did I say that this works for an ideal transformer? Well, in an ideal transformer, your magnetizing inductance is infinite, which means you actually aren't changing the flux level in the core. And a way to visualize this is that your primary and your secondary coils have essentially infinite turns. So when you integrate Vp divided by Np, or Vp divided by infinity, you get no change in flux in the core. But in an actual transformer, you have a finite magnetizing inductance. And so you have to ensure that in a steady state sense, in an average sense, you're not applying any net voltage. The voltage across a coil of a transformer, the average voltage across a coil of a transformer has to be 0 or your flux will walk off to infinity. This is the same rule as we talked about when we were analyzing inductors, how the average voltage across our inductors had to be 0 over a switching period, or our inductor current would walk off to infinity. So this is a direct parallel because the physics are the same. An inductor is actually a magnetic device that has a flux in it, and we have to make sure that we don't exceed the maximum flux in iron material where the iron eventually saturates. So what do? Well, we add what is called a demagnetizing winding to the circuit. So we'll now sketch the circuit with the demagnetizing winding. So I've made a few modifications to the circuit. First, I've added this third winding, this tertiary winding or demagnetizing winding, on the core. I've placed a diode in series with it, and this diode is labeled as D3. Second, I've added a diode in series with the secondary of the transformer, labeled as D1. And you'll see why this D1 diode is now necessary. Let's break this converter operation down into a few states. So in previous converters, we've talked about there being only two states, when the MOSFET is on and when the MOSFET is off. Here we have three states because of the conduction status of the diodes. So the MOSFET is either on or off, but some of the diodes are now going to turn on and off based on demagnetizing the core. And for each state, I'm going to label the three diodes with blanks, and we're going to determine whether the diodes are on or off as we analyze the state. So in state 1, our MOSFET is on, and we're going to create rows spanning these three states that show the equivalent circuit of our transformer connected to the primary, the first secondary, which is our demagnetizing coil, and the second secondary, which is actually the output stage of our buck converter. So starting with the primary, we have our input voltage connected across the terminals of our transformer because the MOSFET is shorted. So again, we've shorted our MOSFET, we've turned our MOSFET on, and clearly our input voltage is now connected across the terminals of our transformer. And from there on out, we've just drawn the equivalent circuit of the transformer that we've been working with in the last couple of videos. Next, we're going to draw the equivalent circuit as seen by this coil here, the demagnetizing coil. And so you can see that in this circuit, at this time when our MOSFET is turned on, we're going to see a voltage appear at the terminal VD, which is going to be Vp times Nd over Np. So Vd is equal to Np times the transformer turns ratio, which is Nd over Np. And Vp is equal to Vin. So we end up getting this voltage source right here, which appears in series with our input voltage source and reverse biases our diode. So this diode is D3, and we now have determined the state of it. D3 is clearly off because it is reverse biased. Finally, we're going to draw the equivalent circuit as seen from the output stages perspective, so as seen at the terminals of Vs. So in this conduction state, we have Ns over Np times our input voltage. So again, that is the voltage that is seen right here. So Vs is equal to our turns ratio times our input voltage, and that is going to be larger than Vout. So that means that we have a positive voltage appearing across this diode, which turns the diode on. The diode is forward biased, and we now know the conduction state of D1. It is on. And that means that we have a positive voltage across diode 2, and so therefore diode 2 is off. So now, working to the right, we'll draw state 2. But before we do that, let's draw what the voltage and flux waveforms look like during state 1. So in the transformer core, we have a voltage applied across the primary, which is Vin, during the interval of state 1. So if you draw that, And next we're going to draw the flux in our core. Remember that d phi dt is equal to 1 over np times Vn. So our flux is a positive derivative over this interval. And also remember that we have a positive voltage across our inductor, so we can sketch our inductor current below and we can see that it will be rising during this interval. Let's now consider state 2 when the MOSFET is off. So at this time, we actually have no active voltage applied across the terminal of our transformer. But that doesn't mean that there's no voltage there. So the primary side equivalent circuit looks like this. We'll now sketch the equivalent circuit that's attached to the demagnetizing coil. And for reasons that will become apparent in a little bit, I've replaced the voltage source of VD minus with a current source of ID. And we'll see why that is in a second. Now let's draw the equivalent circuit that appears on the output stage. At this point, we're no longer applying any active voltage to our transformer. We're relying on the passive circuit itself, which means that the current through the magnetizing inductance, which was flowing in this direction at the end of state 1, is now starting to decay, and we're going to have a negative voltage appear at our primary, on the primary terminals. That means we're going to get a negative voltage appearing right here in our secondary. And that is going to cause this diode, D1, to become reverse biased. And so therefore we now know that D1 is going to be off, which means that IS equals 0. So now let's talk about why I sketched that current source in the demagnetizing circuit, why I sketched this as a current source. So we know that IT1 has to be 0 because our MOSFET is turned off. And we also know that IS equals 0 because diode D1 is turned off. However, we're stuck with this state where we enter state 2 where our core flux is non-zero at some positive value. And the core flux is supported by the MMFs of coils 1, 2, and 3, divided by the reluctance of the core. Well, the current in coil 1 is 0. We just said that IT1 equals 0. The current in the secondary coil is 0. We've just said that IS is 0. So this means that this flux is supported by the current in our tertiary winding, or our demagnetizing winding. And that MMF appears in the reverse direction. So our core flux is equal to the number of turns of our demagnetizing winding times ID divided by our reluctance, which means that we have a specified value of ID as being our core flux times our reluctance divided by the number of turns. And that means that we have to have a current taking this path here, which is a negative ID current. That current will force the diode to turn on, and we'll see a voltage drop across ID of whatever value is required to turn the diode on. And clearly that voltage drop is going to be equal to a negative V in. So let's summarize here. This was diode 3. Diode 3 is turned on, and we have a negative voltage of negative V in across the terminals of our demagnetizing coil. Now, in the meantime, we've built up a current that takes a path through this inductor. And just as in the buck converter, you can't commutate current instantly, the same is true in the forward converter. So that current needs a path to flow. And diode D1 is turned off, so that is going to turn on diode D2. Let's sketch our waveforms. The voltage acting on our core is going to be a negative V in applied on our demagnetizing wire. And so the derivative of our core flux is going to be negative because we have a negative voltage applied, which means our core flux is going to decay. So the core flux starts at some positive value as determined in our previous state, and then it's going to decay down to 0. At that point, when our core flux has decayed down to 0 Webers, there's no need for a current to flow anymore to support the flux. So we can see that ID becomes equal to 0, which causes our diode D3 to turn off, and that ends this state. This state is defined as having diode D3 on and diode D1 off. Finally, we can sketch our current through our inductor, and the inductor sees a voltage drop of negative V out, just like the buck converter does. And so our current is going to start to decay as well. And just as the flux assumes its value from the previous state, so does the current. So if our current ends at this point right here, it begins at that point in the next state. You can't have current discontinuities through an inductor. The total time that this interval lasts is called the demagnetizing time. That's the time it takes for our flux to decay down to 0 Webers. And I'm adding expressions for the voltage across our inductor down below, just to help illustrate what is going on. Okay, in conclusion, we can add that diode D2 is turned on because it's required to provide a path for the current of the inductor in our output stage. Next, state 3. The MOSFET remains off, but now we've just concluded that diode D3 has turned off because our core is demagnetized. And we can again draw our equivalent circuits. So nothing has changed with regards to the primary side equivalent circuit, except for that there's no action in our core anymore. The core is completely demagnetized, so the voltage across our primary terminals is actually now just equal to 0 volts, because our core is demagnetized. That is, we actually have no magnetizing current left either. In our demagnetizing circuit, we have an equivalently boring situation, because again our core is completely demagnetized, so there's no current and no voltage appearing across the terminals of the transformer coil. And finally, in our output stage, it looks just like a normal buck converter would look, because again our transformer core is demagnetized, so there are no physics taking place with the core. So while we've labeled this voltage source as negative in the previous state, it now becomes equal just to 0 volts. Otherwise, everything remains the same. So in conclusion, diode D2 remains on, diode D1 remains off, and diode D3 is now off. And we can quickly sketch our waveforms, but they won't be very exciting. We have no voltage appearing across any of the transformer coils, which means that we have no d phi dt, so our core flux just remains 0. And our inductor current continues its decay. And this state ends at our switching period, Ts, when we restart the whole system by turning our MOSFET back on and circling over to state 1. So those are the 3 states of this forward converter. We have a state where our MOSFET is turned on, this diode is turned off, this diode is turned on, and this diode is turned off. That's state 1. Next, we turn our MOSFET off, and because we've got a flux in this core that must be supported by a current, this forces this diode to turn on. And that diode causes, by turning that diode on, we have a negative Vin applied across the terminals of our demagnetizing circuit, which causes a negative voltage to appear right here and turns this diode off. And so at this point, current is freewheeling through diode D2 just as you would have in a buck converter when the MOSFET is turned off. And this situation continues until the core flux decays to 0 and this diode turns off. And at that point, we remain in a freewheeling state here because the MOSFET is also off. That is state 3. And finally, the whole system restarts itself when the MOSFET is turned on and remagnetizes the core. So let's draw summary waveforms of our flux, our voltage, and our current over the course of the 3 states. And we'll start with drawing our flux. And basically all we're doing is we're taking these waveforms here and we're just compressing them onto a single set of graphs so that it's easier to look at. So in state 1, our flux starts at 0 Webers and it rises to some value. At that point, our MOSFET is turned off and our diode D3 starts to conduct, our demagnetizing diode starts to conduct, and we enter state 2, which lasts until our core flux is completely decayed to 0 Webers. And we remain in this state until we turn the MOSFET back on and we restart the whole thing. So I can see that I forgot to indicate an interval here. Okay, so our flux is 0 in the core for the entirety of state 3, and then we go back to state 1 where our MOSFET is turned on, and that remagnetizes our system. So our flux pattern looks like this. And just as in the flyback converter, we can observe that we are treating our transformer as a single quadrant magnetic device. We always have flux in the same direction. We don't use both quadrants. Our flux never goes negative. That means that we're not using our transformer very effectively. Since our transformer can take a positive B saturation field and a negative B saturation field, we'd like to see ourselves use both sides of the magnetic circuit. Next, we're going to draw the voltage waveform that we have across our inductor. And we noted that in state 1 we have VL equal to NS, or equal to our turns ratio, NS by NP times our input voltage, minus our output voltage. And then in states 2 and 3, our inductor voltage is simply our negative of our output voltage. This looks like a buck converter with a turns ratio. And finally, we'll sketch our inductor current. And we can label our interval times on here, where state 1 lasts for D times TS, a duty ratio times our switching interval. State 2 lasts for a duration called our demagnetization time. And then finally we conclude at the frequency, at the period of our switching frequency, which is TS. So you can see that there's a maximum duty ratio that we're allowed to have for our MOSFET. And that is limited by the time it takes to demagnetize our core. If we go too long with if we turn our MOSFET on for too long, we don't have enough time to demagnetize our core, and our flux will start walking off to infinity, or will saturate our core. So we can sketch what that would look like here on the right side. And again, we're drawing our flux waveform. We magnetize our core, and then we turn our MOSFET off and we start demagnetizing. But before we ever get to 0 Webers, we turn our MOSFET back on, so we magnetize further, and then we start demagnetizing. We turn our MOSFET off, but before we even get down to what we were previously at the beginning of state 1, we turn our MOSFET back on. And so you can see that our flux is going to walk off towards positive infinity. So this is what happens when our MOSFET on time is greater than the time that is required to demagnetize our core. And this means that we have a certain maximum MOSFET on time that we're allowed to have based on the number of turns of our demagnetizing coil. So if we have a situation where we have the same number of turns in our primary core as in our demagnetizing coil, so that is NP is equal to ND, and we can see that when our MOSFET is on, we're applying V in to our core, and when our MOSFET is off, we're applying a negative V in. So we've got this situation when the MOSFET is on, and we have this situation when the MOSFET is off. We can see that when we have the same number of turns, our demagnetizing time is going to be equal to the time that we have our MOSFET on. That is, the demagnetizing time equals D times TS. And that means that in this situation, we have to keep our duty ratio of our MOSFET below 0.5. So if it takes exactly the same amount of time to magnetize the core as it does to demagnetize the core, we can only magnetize the core over half of the switching interval. Okay, so in summary, we have introduced the forward converter in this lecture. and we've derived its operating principles and waveforms. We've done this by considering a buck converter and deriving what it would look like if we were to insert a transformer into the single pole double throw converter of a buck converter, and then noting that our simple approach to it didn't actually work for a real transformer because of the magnetizing inductance. So we added a tertiary winding, a demagnetizing coil to it, so that the core could demagnetize itself when we turn our MOSFET off. And from there we derived the operating principles of the circuit. We noted there are actually 3 states in the circuit depending on the conduction status of the MOSFET and the various diodes. We've drawn the equivalent circuits using the transformer equivalent circuit. We've sketched waveforms, and we finally noted that there exists a maximum duty ratio based on the turns ratio of our demagnetizing coil to our primary coil of the transformer.